So the previous lecture introduced the idea of a forced oscillation. And so one thing that could also happen is a damped oscillation. And that'd be, for example, if you had your mass here and it's in a fluid that has viscosity. Now remember, the force of viscosity is minus BV, whereas the spring force equals minus KX. And so the total force acting on this thing as it's moving back and forth is minus KX minus BV. So what do you do in the full-blown equation, in which the second derivative here is equal to minus B over M dx dt minus K over M x. So this is the full-blown equation. So what do? Well, what you do is you guess it's a combination of the two. So you might guess that x is some amplitude e to the minus b over mt cosine omega t. Okay, so you plug this in and you realize it doesn't quite work. Okay, it comes really close to working, but it doesn't quite work. And what does make it work, though, is if you have a 2 right there. Okay, and so now it's going to work, and then omega turns out not to be the same omega we had before. It's not K over M. You work this out, and so it turns out it's K over M minus B over 2M squared. Okay. That makes it work. And so that is the solution to this differential equation. And we call this the damped oscillator. Okay. So now notice, what we've got here is we've got that x is now some amplitude e to the minus b over 2mt cosine omega t. Okay, and omega is square root K over M minus B over 2M squared. And so you look at that and we say, okay, what if B is small? So if B is small, then this is almost going to be the same frequency that you had before. And so if B is small, T has to be big in order for this exponential to start dropping. And so what would happen is you would look at that and it would look like cosine that's just gradually getting smaller. Okay, so we call that underdamped. So this would be an oscillation that's gradually getting smaller. So it'd be like saloon doors. You walk through and they swing back and forth, and they gradually swing less and less and less. This would be like an ordinary pendulum. You pull it off the side, it swings back and forth, but eventually air resistance slows it down. And so this would be an underdamped situation right there. Okay, and so we look at it and say, well, that's cool. Okay, but what if B is large? So omega, so again, we've got that x equals a e to the minus b over 2m cosine omega t. So, and then omega was square root k over m minus b over 2m squared. So what if b is large? If b is large, we got a problem here, because now that is negative. So we have square root of a negative number. That is an imaginary number. Now, there's an interesting thing that you can actually deal with an imaginary number in a cosine, okay? Because it turns out you can write cosines and sines as e to the I theta. And so, or combinations of e to the I theta, e to the minus I theta. And so what that does is that if you have I times I, that's a negative number, it's a real number. So what will happen is that you will end up with basically something that is is almost e to the minus b over 2mt up here. And so what that's going to do is that's going to be something that's going to be slightly off. So we have e to the some number here that gradually decreases. So what's going to happen is you have it here and it just gradually drops down and it sort of asymptotically approaches zero. We call that overdamped. Okay, so overdamp would be like a regular closer for an automatic closure for a door. You don't want it to swing closed very fast. You want to open the door, walk through, and it slowly closes behind you. So overdamp would be something you pull out of position and it takes a long time to get back to position. And so that would be a case of overdamping. And there are times you want something that if you put it out of position, it takes a while to get back. And so there are times you won't. Well, again, so x equals e to the minus, or a e to the minus b over 2mt cosine omega t, where omega is square root k over m minus b over 2m squared. Now, what if b is just right? Okay, so the Goldilocks b. That would be if omega is 0. Because we had omega, we have b small, b big. What if b is right in between? So what if b is such that k over m minus b over 2m squared is 0? So that's k over m minus b squared over 4m squared equals 0. So that m cancels right there. And so we move b to the other side of the equation. So b equals the square root of 4mk. Now, if b is equal to that, okay, or 2 square root mk. If b is equal to that, then omega is 0, and so we end up with a e to the minus b over 2mt. That's exponential decay. So in this case, you pull something out of position and it drops back exponentially fast where it started. And so we call this critical damping. So the x will be some amplitude, how far you put it out of position, e to the minus b over 2mt. Okay, and so b is going to be equal to 2 square root mk. And so that's the critical damping. Now what's an example of that? Well, imagine a car. Okay, so we have a car driving along. We got the suspension, which are the springs here. If you did not have a suspension on the car, then if you hit a bump, then it would jar your teeth out. So what happens is you hit a bump, the wheel is able to move up, go over the bump, but after you go past the bump, the car is going to bounce up and down. In fact, that often was the case in early vehicles. And so to dampen the oscillation alongside the suspension is basically a fluid-filled cylinder with a plunger in it. And that has a viscosity right here. That's your shock absorber. I always thought it was a dumb name because the shock absorber does not absorb any shock. The suspension absorbs the shock. The shock absorber dampens the oscillation of the suspension. But they didn't ask me. And so the shock absorber is balanced to the mass of the vehicle and to your spring constant. And so what happens is that you want this to be just right. So if the vehicle, so you balance it for the vehicle, and it's gonna be balanced. So you, for example, if you have a car and you overload the vehicle, in other words, you put too many people in the vehicle, too much load in the car, what's going to happen is that now B is too small because it should have been bigger. And so an overloaded car tends to bounce a little bit. Also, if your shock absorbers are leaking fluid a little bit, then B gets less, and again, you're underdamped. Okay. Now think about a pickup truck, for example. For a pickup truck, okay, the idea of a pickup truck is that the idea is supposed to be carrying a load right here. And so the B is based on a load right there in the bed of the truck. a lot of people drive around pickup truck without a load, and so in that case, B is now too big, and so you're a little bit overdamped. That means that the pickup, while it's empty, is going to be a rougher ride than if it has a load in it. If it has a load in it, then B's proper, and so you end up with a smoother ride. Now, of course, you do have more expensive vehicles do have the ability to adjust the shocks, and so the adjustable shocks can be adjusted for the mass of the vehicle, which gives you a smooth ride no matter what. That's those kind of things are a little bit out of my price range, but they do exist. And so this would be an example of application of overdamping, underdamping, and critical damping. And so with just shock absorbers in cars. And so I thought that'd be an interesting example. Now, one of the things we realize in physics 2 is that we end up with electrical circuits that have electric charge in there, and we realize that the second derivative of the electric charge is proportionate to the first derivative and to the first derivative and to the charge itself. And so that gives you back to this damping situation. And that damping situation or oscillations there, you can have an oscillating circuit, that's like the tuning circuit of a radio, or a damping of an oscillation, and that would be something that you'd intentionally design into a circuit so that when you turn something on or off, it as quickly as possible reaches either full potential or zero. And so again, the same basic ideas come back again, even in electrical form. And so you now have learned about damped oscillations. Okay, underdamped. Okay, B is too small, and so they oscillate. Overdamped. B is too big, and so it takes a long time to get back to equilibrium. And then critical damped, in which B as quickly as possible returns to equilibrium. And so these are the three basic conditions for damped oscillations.